All right. So thank you guys, everybody, for joining my session. My name is Audrey Long, and this is Threat Modeling Star Wars Edition, or Threat Modeling 101 Star Wars Edition. So before we get into it, let me tell you a little bit about me. So I just got my master's degree from the Johns Hopkins University in cybersecurity. Before that, I have my undergrad from the University of Cincinnati in computer science. Currently, I'm a senior security software engineer at Microsoft and a very recent Women's Techmaker ambassador for Google. So aside from, my day job, I love to cook, create, and learn new things. Big nerd, as you can tell from my session. So if you guys want to talk about 3D printing or PC gaming or nerdy books, I'm all about that. So please feel free to reach out and we can talk about any of these good, goofy things. So a little bit about me, what I do in my day job. So I'm a security and identity subject matter expert. What I do specifically is I help customers understand their security and identity needs when they're migrating their code or creating net new code in Azure. So what I like to do is I'll sit with folks and I will actually do a lot of threat modeling. And I will also help them create security architecture, code up their solutions, really anything that they need help with in the identity and security space. So that's what I do in my day-to-day role. So this session, we're going to be talking about threat modeling. So what exactly is threat modeling? So threat modeling works to identify, communicate, and understand threats and mitigations within the context of protecting something of value. A threat model is a structured representation of all the information that affects the security of an application or a system. In essence, it's the view of the system and its environment through the lens of security. Threat modeling can be applied to a wide range of things, including software, applications, systems, networks, distributed systems, Internet of Things devices, business processes. Really, anything can be threat modeled, and I'm pretty sure I have threat modeled about everything. All right, so who should be threat modeling? So I see a lot of different folks in different roles doing threat modeling activities. For the organization that I'm in, it's primarily an engineering organization. So I see a lot of software engineers actually doing some threat modeling. And that's what I try to skill people up on, their software engineers, so they can actually get ahead of these threat modeling activities before they actually get to building code. But really, I see lots of people doing it. Security engineers, architects, program managers, software testers, and really anybody with a working knowledge of the system can create a threat model. All right, so before we get into, threat modeling practices and then actually going deep into threat modeling the Death Star, let's give you a little bit of security context here. So security requires a particular mindset. Good security professionals see the world differently. They can't walk into a store without noticing how they might shoplift. They can't use a computer without wondering about all the security vulnerabilities. They can't vote without trying to figure out how to vote twice. We just can't help it. This type of thinking is not natural for most people. It's not natural for engineers. Good engineering involves thinking about how things can be made to work. The security mindset involves thinking about how things can be made to fail. It involves thinking like an attacker, adversary, or criminal. You don't have to exploit the vulnerabilities you find, but if you don't see the world that way, you'll never notice most security problems. By adopting a security mindset, you emphasize the attacker, their motives, means, and all of the ways they can wreak havoc in the system. This approach looks at entry points and system weaknesses and allows you to focus on critical assets holding highly confidential data for your system. So when those weaknesses are discovered, emphasis is placed on protecting those assets instead of the entire system. So here we can see the core algorithm of developing threat models within the commercial industry. So anything can be used in regards of threat modeling process. However, this is a very condensed, very straightforward and easy algorithm that can be applied to create threat models in any kind of system or environment. So let's kind of go through them one at a time. So the first phase is analyzing the system. And we like to also call this the design phase. And it's the starting point for your threat modeling activities. You'll gather as much data as possible about what you're building and what you're using to build it with. And the goals for this step include developing a clear picture of how your system nominally functions, enumerating services consumed by your system. So we're really trying to get deep inside of the architecture here and understand what services are being used and how are people going to actually use those services. Investigating environment assumptions and security controls, gathering system requirements and documents, and identify those key security stakeholders. Because too many times I've actually gotten into threat modeling conversations with customers, and if those key security stakeholders aren't there, then you're just wasting your time on creating some of these artifacts sometimes. So we just got to make sure the right people are in the room when you're creating them. Now, the step 2 is to actually design a data flow diagram. So a data flow diagram, or otherwise known as a DFD, is a visual representation of any process or system flows of information inside and outside of your system. By mapping out your processes or systems flow of data, DFDs can help you better understand your process or system, uncover its kinks, improve it, and it can also help you implement a new process or a system. So the high-level goals when designing a data flow diagram include to understand the user and the system scenarios throughout the system. We live in the world of software. Lots of people like to automate machine flows or workload identities or whatever you may call it in your organization. But those are also important to understand. How do we understand the data that's going in and out of that? How does CI/CD do it behind the scenes? How are we doing some of our Git jobs? A lot of these get left on the table, and these are really important to capture. We also want to establish those trust zones and boundaries within the system, identify those user permissions throughout the system's lifecycle, and to investigate protocols being used inside and outside of the system being designed so we have a better understanding of that auth N and auth Z story. Now, the third phase in creating our threat model is to identify threats. This phase is where you use the data flow diagram to find potential threats against your system. We will use a threat modeling framework to help you find the most common threats and ways to protect against them. At the end of the day, a threat modeling framework is essentially a series of rules and guidance associated around teasing out threats within a system or an environment. Here you can see some of the high-level, most commonly used threat modeling frameworks. So at Microsoft, we traditionally like to use STRIDE, which is an acronym for the 6 main threat categories to provide an extensive but not exhaustive list of threats. And we're actually going to be using STRIDE later on in the slide deck to demonstrate how we're threat modeling the Death Star using this framework. Also, threat modeling is a great technique to help you find issues early on in development cycle. And choosing the right focused approach helps you tailor the threat modeling exercise. So basically, for these threat modeling frameworks, finding the one that works for you is going to be key because they're all a little bit different, and whatever helps you find and identify those threats easier is going to be successful for you in the long run. All right, so step 4 here is to create mitigation strategies. This is the phase where all fates of threats are decided. Each threat modeling framework should map to security controls within your environment, which offer different functions and different types to choose from. Once the mitigation candidates are created, a criticality or a weight should be assigned to each one to determine which mitigations should be implemented right away, along with the complexity and time to fix each mitigation candidate. In this phase, the high-level goals are to measure each threat against a prioritization bar or security bug bar. That's what we like to use at Microsoft. Track each threat as a task or a work item in a backlog. This one's really important, guys, like making sure that we actually have this security work documented in a place that is actionable and can be iterated on is really, really important, because a lot of the times I see security work falling through the cracks because we don't do a great job at ensuring that folks can actually pick up the work that we've discovered. Generating control system recommendations mapped from those threat modeling frameworks, and selecting one or more of the security control types and functions to address each threat. And last but not least, the last phase in our threat modeling process is to continuously iterate and verify. The verify phase is the last step, which often happens before the system is deployed. It involves ensuring requirements are met, assumptions are validated, and security controls are in place. And some of the high-level goals here are to confirm all previous and new security requirements are satisfied for the system, configuring those cloud service providers, operating systems, and components to meet security requirements, and to assure we address all of the issues are addressed with the right security controls and taking the system through manual and automation verification before deployment. Also, something I really like to call out here on this slide is a lot of the times I see folks creating threat models and not iterating them throughout the life cycle of your engagement or in your project. This should be treated just like any other DevSecOps process. We need to continuously iterate, verify, and update because the system's always going to change. And if you only create that threat model one time without updating it, then you're going to unfortunately be behind. And just making sure we do that as well as updating and validating our security and just architecture design documents is going to be really key in moving your projects forward. All right, so we just went over at a high level the security strategy that I like to look at when going through and creating those threat models. So let's just kind of look at it in a high level before we go on to the next section, which is actually threat modeling the Death Star. So first phase is to identify the security stakeholders. Then we'd like to evaluate the customer requirements and that architecture in that design phase. Generate that data flow diagram, understanding the auth-in, auth-z story and protocols for each of those flows, both human and machine users. Generating those threat model mitigation strategies with frameworks and identifying those threats. And then creating security backlog items from those threat model mitigation candidates. Now that we have all of that information at a high level, we can now go and threat model anything. And as all of you are excited for, that's what we're going to do today in threat modeling the Death Star. All right, so we're going to map back to that core algorithm to doing this exercise with the Death Star. So phase number one is to analyze the system. According to the US government, and no, really, the US government did this actual analysis, the first Death Star would have cost $852 quadrillion to construct. And the Death Star took 20 years to build because of its sheer size and complexity. So now the question comes, why didn't a thorough security review happen for this humongous project? So the Death Star is a very complex piece of machinery which contains very intricate services which rely on each other to achieve total destruction and induce fear throughout the galaxy. The Death Star's main purpose is to function as a mobile platform for its main weapon, the super laser. The Death Star structure is basically an enormous housing unit for the super laser and the reactor that powers it. And just for clarity too, we're actually going to be threat modeling the DS-1 orbital battle station, which is the first Death Star, which is in episode 4. So at a very high level, the Death Star is made out of 4 major components: the battle station, the super laser, the propulsion system, and the hypermatter reactor that powers it all. So let's take a very high level look at these components. So the battle station is a huge equilateral trench that splits the surface into 2 hemispheres, and this trench is used to house many of the Death Star's main systems, which also includes thermal exhaust ports, which are outlets for dissipating excess heat produced by the large energy reactors used on board starships and space stations or in certain ground-based structures. The super laser has a massive lens built on a huge synthetic focusing crystal. The lens is known as the eye and is surrounded by 8 trebuchet lasers. The Death Star's super laser derives power directly from the hypermatter reactor, and the lasers convert the power and focus that full power of the reactor to create the beams. The propulsion system is the Death Star's real space propulsion system and is made up of a network of ion engines that use converters to transform reactor power into thrust. The engine thrusters are primarily along the lines of the equator of the station. In the hypermatter reactor, the greatest challenge in designing the Death Star was not creating a cannon big enough to fire a beam that can destroy a planet, nor was it creating a battle station the size of a small moon. But the greatest challenge was always powering a cannon big enough to fire a beam that can easily destroy a planet and moving the battle station that's the size of a small moon. And to answer both of these problems, it was solved with the invention of the hypermatter reactor. Okay, so now that we have all of the design, let's go ahead and take a look at the data flow diagram that I've designed for this system. So here you can see, unfortunately, in this universe, there weren't any machine flows, but there were user controls. So a lot of the users could interface with the command station computer. And a lot of the inputs that a user could actually put in this computer was to fire the super laser at a desired target, remotely control the station's deflector shields and super laser, align the super laser to point at a target, gather system telemetry data, activate tractor beams, fire ion cannons, and jump to warp speed, as well as engaging engines and whatnot. And a lot of those inputs really go through one centralized station, which is the command station. And those subsystems, such as the hypermatter reactor, the laser ion cannons, the sensor arrays, the drive thrusters, the propulsion system, all get interfaced through one location. Now that we have a good understanding by having a data flow diagram, this is what I like to call a threat map. And at the end of the day, a threat map is a very high-level attack tree. Now, in classical threat modeling, attack trees have one goal node at the top, and then you can traverse each tree to see how an attacker can actually get to that goal node of exploiting the system. And in this kind of a demonstration in this picture, I like to show high-level attack tree, which has the high-level attack goal nodes of each of those trees. I think it's a very compelling photo, and it also really gets you thinking about all of the threats that are available in the system. So let's take a quick view at what are some of the threats in the system that we see here in this photo. So a threat actor can disable the ion cannon systems, can disable the tractor beams, exploit vulnerability by destroying the reactor, tamper with sensors to mislead battle station readings, disable the protective shields, command and control the station computer, mind control officers if you're a Jedi, of course, but we are in the Star Wars universe, so this is definitely a possibility and needs to be threat modeled, and then jam communications throughout the ship. So after we've identified all of these threats, now we like to create some of those mitigation strategies. So first, let's talk about vulnerabilities. A vulnerability is any weakness, known or unknown, in a system, process, or other entity that could lead to its security being compromised by a threat. In this example, Luke Skywalker is exploiting the thermal exhaust vent by launching torpedoes into the vent, impacting the core and triggering a catastrophic explosion. An easy mitigation for this could be to eliminate the 2-meter wide thermal exhaust port or safeguard this exhaust vent with extra defenses and perimeters. Now, for the rest of this, let's actually use Microsoft's Stride threat modeling framework to go through and identify some of these other threats that we've identified from the threat mapping activity. So here, let's talk about spoofing, and that's the first thing in Stride. S stands for spoofing. It's a property of authentication. Spoofing the Death Star's sophisticated security systems could potentially be vulnerable to spoofing attacks. Intruders might impersonate legitimate personnel to gain unauthorized access to critical systems, causing havoc. Understanding these vulnerabilities allows us to design authentication mechanisms that prevent unauthorized entry. And in this example, we see it throughout all of the Star Wars movies, impersonating stormtroopers to hijack communication systems and save princesses, as done by Han Solo and Luke Skywalker in Episode 4. A potential mitigation could be authenticating principals, users, or machine identities by enabling more robust and multiple identity mechanisms, such as multi-factor authentication. Now, T stands for tampering, and this is a property of integrity. where tampering involves an adversary modifying data, usually as it flows across the network, in memory, on disk, or in a database. So the immense size of the Death Star brings with it the challenging of ensuring the integrity of its own components. Tampering threats could target critical systems or manipulate important data, leading to disastrous consequences. Implementing tamper-proof technologies and continuous integrity checks would be essential in mitigating this risk. In this example, Obi-Wan Kenobi tampering with the tractor beam system to allow the Millennium Falcon to fly into the sunset is a great example of tampering. And as we previously called out, some mitigations could include adding validation, such as credentials and codes, and safeguards, such as cameras, guards, and limiting that access around the machinery to tamper with anything such as a, tractor beam. Now, R in STRIDE stands for repudiation, and this is a property of non-repudiation. And this threat involves an adversary denying that something happened or claiming to not have performed an action. In the realm of space warfare, ensuring non-repudiation is very paramount. A potential threat lies in malicious actors denying their involvement in destructive activities, making it crucial to establish robust logging and audit mechanisms to track actions and maintain accountability. In this example, Han Solo saying, "There's a very dangerous reactor meltdown and attempt to stage a divergence to save the princess." Some mitigations, as previously stated, include ensuring that proper observability is in place to track down adversarial behaviors and logging those behaviors so we can potentially detect threats early on. Now, I stands for information disclosure, and it's a property of confidentiality. For the definition of information disclosure, it's exposing information to someone not authorized to see it. The Death Star's vast repository of sensitive information, including plans, defenses, and personal data, could become a prime target for information disclosure threats. Proper access controls, data encryption, and data compartmentalization can help safeguard against such vulnerabilities. In this example, we see Jyn Erso relaying critical Death Star vulnerability information to the Rebel Alliance as seen in Rogue One. The mitigation also could be around thoroughly understanding your asset inventory, and public exposure is also very important to understand so we can mitigate for this threat. D in STRIDE stands for denial of service. This is a property of availability. And in this example, we deny or degrade services to users. So the Death Star's operational continuity is imperative for the Galactic Empire. However, a DOS attack can disrupt its functions, rendering it vulnerable to attacks. Employing load balancing, redundancy, and DOS mitigation techniques would be vital in ensuring uninterrupted operation. In this example, we see Chewie jamming transmission channels for a TIE fighter. Ensuring that communication channels are encrypted and only verified users can access those channels is also paramount. Also, practicing redundancy, such as backup channel availability if one channel goes down. So we also have the constant communication. Now, last but not least, E stands for escalation of privileges, and it's a property of authorization. An elevation of privileges, they involve adversaries being able to do something or obtain the rights to do things which they have not been authorized to do so. Preventing unauthorized personnel from gaining unauthorized access to sensitive areas is crucial. Elevation of privilege threats could enable attackers to manipulate the station's operations from within, and implementing the principle of least privilege and rigorous access controls can counteract those risks. In this example, R2-D2 hacking into the star system to open doors and extract information, as we have seen pretty much every single Star Wars episode or every single Star Wars movie. Some droid is extracting information in some way to help our heroes out in any of the storylines. The mitigation here can be put checks to verify appropriate access levels are in place for each request that's going through the system. And last but not least, we must continuously iterate and verify. The Death Star's vulnerabilities may be fictional, but the lessons we draw from them are highly applicable to real-world security challenges. By employing threat modeling, organizations can systemically identify potential threats and develop strategies to mitigate them, ultimately enhancing their security posture. As we walked through the Death Star's vulnerabilities through the lens of Microsoft Stride components, we were reminded of the importance of proactive threat modeling. By understanding and addressing potential security risks in advance, we can bolster our defenses, protect our systems, and ensure the integrity of our technological advancements. May this talk serve as a reminder that even in the world of science fiction, there are valuable insights to be gained for the realm of security in our own galaxy. So here I wanted to share with you guys some learning materials. So here are links to the Microsoft Security Development Lifecycle, otherwise known as the SDL. And it is the lifecycle that we like to give all of our software engineering teams here at Microsoft to follow. And it is very comprehensive. It has a lot of steps that we shall do in order to deploy code to in any kind of Azure environment, for example. There's also threat modeling security fundamentals training on Microsoft Learn. This is a free module where you can go in and learn the basics of threat modeling. There's even a little Microsoft threat modeling tool that you can gain access to. Not my favorite tool, I'm not going to lie. I actually don't like to use tools at all when doing threat modeling. I think it's more of a valuable exercise for yourself to do it by hand, but that's my 2 cents. Here's also some links to some really popular threat modeling frameworks, as well as government guidance on how NIST likes to create data-centric threat models. And I would like to say thank you guys so much for coming and listening to my talk. This has been really great. Unfortunately, I cannot join the networking session I am on a really tight schedule right now. However, please reach out to me on LinkedIn, linkedin.com/AULong or Audrey Long. If you want to find me on LinkedIn, I'm really happy to set up some time to chat with you guys. If you have any questions regarding threat modeling, or if you have any questions at all. So I'm really, really sorry I can't join this networking session, but really happy to answer any questions after this. And thank you guys so much. May the force be with you.